calculating internal resisting torque. If you say we have a section like this, a large shaft, and this is the cross section of the shaft, and this is a test here. Now if we apply some torque like this, external torque, you can imagine that there is a bunch of CD disc like that, and then if you apply that external torque T, you can imagine that each of these CD discs, they are trying to slide against each other. So what is the shear stress between that plane, that circular plane? This is what we're trying to calculate here. So let's draw a circle, kind of exaggerated section like that. We're just taking one CD disc and see trying to calculate. So take a small section like the and very small area here, A, at a distance of R. This is R distance from the center O. Now the radius, as said, define that as by C, the distance from the center to the outer fiber of the metal or wood, whatever. Now the shear distribution will be highest in the outside. You can easily imagine that by, if you try to break a piece of weak wood, twisting, you will see that it's gonna crack from outside, start to crack from the outside, and then it will break eventually. So the highest torque shear stress will be outside. So that's shear stress tau, as highest at the outside. And then this area, so if we want to calculate how much force on this area, we have the shear stress. We need to know the shear stress, the outside shear stress, the maximum shear stress is tau at a distance of C. So at C distance we have tau shear stress. So at R distance it will be tau by C times R. So that will be shear stress at R distance. So we can say tau R, maybe stress, like that. So if we have the stress, now we can calculate the force. Force is equal to stress times area. So think about, we are talking about that small area. So stress at a distance R is tau by C times R times the area. Now we know the force at a distance R. So the torque we can calculate by multiplying force times distance. In this case, the force is tau by C times R times A. So this is our force, and then the distance is R from the center. Let's bring that here. So torque, that is the internal resisting torque, by the way, because we are looking at inside that piece. So that torque T, internal resisting torque T, tau by C A R square. That is a distance R. So on that is small piece A, on the small section that we cut in the at a distance R. Now if we want to calculate the total torque on that disc, we can sum all the torque, tau by C A R square. So we can say tau by C is basically constant summation of AR square. If you remember what is summation of AR square, so total torque is that summation of AR square is basically polar moment of inertia, which is expressed by Z. So that is the first relationship to get internal resisting torque. Now, if we want to calculate, say for example, we are interested in calculating shear stress instead of torque, and torque is given. So shear stress, then we can solve for shear stress. That will be TC by J, like that. So that will be our equation number 2. See if I have enough space here to show that design equation. Now we know that Z, polar moment of inertia, the formula for that is, for a circular section, J is equal to pi d power 4 by 32. So if we plug that J, if we bring the J here, and we can write the equation like J equals TC by tau. So if we replace J with that, pi d power 4 by 32 TC by J, and then C, we can replace that by d by 2. As you can see, for a circular section, C is basically radius. So if we solve for diameter, we'll get something like this: 316T by pi shear stress. That will be allowable shear stress. Now this piece is not J, this will be shear stress, like that. So pi allowable shear stress. This is a design problem, so we want to find out what would be the diameter of a shaft. So that would be the equation number 3. So you want to find the diameter of a shaft, we need to we have to be within that limit of that material, the shear stress allowable, instead of just a shear stress for the general formula like in other 2 cases. But this one is a design. When you are asked to design a shaft, then you use this formula, and then if you don't use the allowable shear stress, the material will eventually break, so the diameter will come not accurate. So use the allowable when you're asked to design something. And then these 2 are basically calculate torque, internal resisting torque, or shear stress, like that. So that's about the torsional shear stress, torque, and design formulas.